Today's video will demonstrate how to implement the graph using the set of edges implementation option. Hello, I'm James Helfrich. We have 4 implementation options for the graph. One of them, the set of edges, is optimal when we have a large number of vertices but a small number of edges. This video will demonstrate how to use that implementation. There are 4 implementation strategies for the graph. The first is interconnected nodes, where every vertex on a graph is represented as a node, and that node has a collection of pointers to other nodes, which represent vertices. The second is a set of edges, where every edge in the graph is represented by a 2-vertex pair. The third is an array of sets, where every source vertex can have a set of destination vertices, and if there is a destination vertex for a given source, there's an edge there. And the final is a grid, and this is a 2-dimensional array of Booleans, where the horizontal axis is the source vertex, and the vertical axis is the destination vertex. If there is a true in that source destination location, then there's an edge. If there's false, there's not. We're going to focus on the set of edges implementation today. First, let's take a look at the UML class diagram. We have a graph, and that graph is going to have a collection of normal public interfaces, a constructor and assignment operator, empty, size, and clear. It will also have an add between a source and a sink, a remove between a source and a sink, an is edge between a source and a sink, a find all the edges for a given source, and a find path between a source and sink. Each of these requires a vertex. Now, notice how a vertex is not stored within the graph, but rather is utilized by the graphs. So we have the arrow end cap. Our member variable edges is a set, and there's going to be exactly one set, and this set is going to be a template. And what's the template going to be? Well, it's going to be a pair of vertices. And remember, a pair takes 2 templates, and both of these are going to be vertices. To see how this works, I have a graph of 5 vertices. When I say graph of G, then I'm going to have 5 vertices, and my set will be empty. When I'm going to add a vertex between 0 and 1, then vertices 0 will have an arrow to 1, and then I'll have one edge, 0, 1. When I add vertex 0 to 3, then the source is 0 and the sink is 3, so there's an edge there. And now I'm going to add 0, 3 to my set of vertices. 2, 1 goes to 2, 1, and 2, 1 gets added to my set. 3, 2, 3, 2 gets added to my set. 4, 0, 4, 0 gets added to my set. 4, 2, so source is 4, destination is 2, and then 4, 2 gets added to my set, and finally 4, 3 gets added to my set as well. The result is 1, 2, 3, 4, 5, 6, 7 edges in my graph. So let's take a look at the pseudocode for the main algorithms for my graph. The first is edge. I want to see if there's an edge between a source and a sink. So the way I do this is I'm going to create a pair of my source sink, and that's the edge query, and I'm going to see if my edge query is in my set of edges. Now, sets find will give me an iterator. If that iterator is end, there is no edge. If it's anything but end, then I have an edge. Notice this is going to be log n, because sets find method is log n. The next function is called find edges. I want to find all the destination vertices corresponding to a given source vertice. To do this, I'm going to iterate through all the edges in the collection of edges, and that element is going to be called edge, and edge is going to have a source and a sink. Now, if the edge that I iterated for has a source that's the same as the source I'm looking for, then I'm going to insert that edge's sink into my set return. This is going to be O sub n to iterate through all the edges in the collection, log n, because it's going to take me log n to insert this into my set return. Next is insert. I want to insert a new edge into the graph. I'm going to have to create a pair from the source and sink, and I'm going to insert that pair into my edges set. This is log n because inserting an element to a set is logarithmic. To remove, I'm going to create a pair from my source and sink just like before, and I'm going to call sets.remove, which will remove that element from my set. This is log n also because sets remove is logarithmic. Okay, try this example on your own. Given a graph that has 1, 2, 3, 4, 5 edges, can you draw the graph corresponding to it? Pause the video, try this, and then resume the video. Okay, here's my solution. So initially, I'm going to have 4 vertices, 1, 2, 3, and 4. I'm going to start with 1, 2, so source is 1, destination is 2. Then 1, 3, source is 1, sink is 3. 2, 3 goes from 2 to 3. 2, 4 goes from 2 to 4, and 3, 4 goes from 3 to 4. And there is my graph. In this next problem, I'm going to have a graph and to see if you can find a set of edges. Once again, pause the video, try this yourself, and then compare your solution against mine. Okay, we'll start with vertex 0. 0 has an edge to 1, 2, and 4. Therefore, I'm going to add 0, 1, 0, 2, and 0, 4 to my set of edges. Then 1 has an edge with 3, so 1, 3. 2 has an edge with 4, so 2, 4. 3 has two edges, to 1 and to 6. 4 has several edges. You see here, 4 to 0, 4 to 5, and 4 to 7. 5 has 1, 2, 3 edges, to 4, 6, and 7. 6 has one edge, 6 to 4. And 7 has one edge, 7 to 2. And that's my set of edges. You can learn more about graphs, including the set of edges implementation, in the Sets chapter of the C++ Data Structures textbook.